Hi, welcome to Module 7 in Lecture 8. Having now talked about probability mass functions, two different classes of those in the previous two modules, we're going to again focus on more general ideas. Not that probability mass functions aren't general, but instead of looking at particular mass functions, we're going to look at the more general idea of expectation. An expectation of a random variable is exactly what it sounds like in English. It's what you would expect to observe if you happen to observe a random variable once, right? It's your expectation of what you would see if you observe the random variable once, given that the random variable is distributed in some fashion. That's all it is. We typically refer to it as E. If we're totally sure there's only one variable involved, we can just write E with brackets. That means the expectation of the thing in the brackets. This thing can be very general. It can be just a variable, it could be a function of that variable. We'll talk about different cases of this later. But E here just means expectation of the thing in the brackets. If we're not sure about the variable, we should put a subscript here to illustrate that the expectation occurs over x, over the variable x. And I shouldn't have had the x in there. This can be over anything inside the brackets. It could be over x or anything else. When we do have an x there, when we have an expectation over a single variable, which is the variable distributed according to the probability mass function or probability distribution function, we call this an expected value. It's the expected value because it's the expected value. Remember, the value of a random variable is the particular value, the particular number that pops up when you happen to realize that random variable. The expected value is the realization we most expect. Very often, and so let's go into what it actually means. Let's do a simple example first. The expected value in general, of a function f of x for a discrete function is equal to the sum over I of xi times the probability that the random variable, f of xi, times the probability that the random variable x equals xi. And the sum means you take it over every I. So let's break this down a little bit. What you're saying is that the expected value of this function of x is equal to the function evaluated at a particular point, a particular value in the support of the distribution, weighted by the chance that that value actually occurs. And you sum that over all possible values that could in the support of the distribution. That's what an expected value of a function is. A simpler version of this is just the expected value, period, no function. The expected value of a variable, by the same exact logic, is just the sum of xi times the probability that x equals xi. And there you go. That's all it is. Now, this might still seem kind of complicated, but actually you've seen this before. This is just a weighted average. If I had the probability that x equals xi were constant, were uniform over all possible xi in the support of a distribution, we'd have what's called a uniform distribution, which we'll talk about later. But that kind of distribution would have each probability of being each probability will be the same for every xi. And let's say you had n things, then each one would have to be 1 over n, because if they're all the same and they have to add all up to 1, then 1 over n plus 1 over n and so on, n times equals 1. So then we would have 1 over n times the sum of xi. And this is the definition of an average, of a mean, an arithmetic mean. You add all the individual values and you divide by the number of elements in the support of the distribution, number of values in the support of the distribution. This down here in the bottom is just an unweighted average. This thing over here that I've written over partway is a weighted average, because the probabilities are not necessarily all equal, not all uniform. You can weight certain values more than other values. But it's the same exact conceptual idea. And this is an expected value. it's adding up all the different values weighted by the chance they occur in the distribution and adding them together, and that produces the expected value of a function. And again, when you have all the probabilities are uniform, the same, then you get a straight non-weighted average, which you've seen before many times. Okay. When do you use this stuff? You use this stuff many places, but one place that comes up quite often is in game theory when you're trying to figure out some kind of expected value of, say, a lottery. So for instance, and we talked about this before a little bit already, for instance, let's say I have some lottery, a straight lottery, a real lottery, in which you win 0 with probability 0.99 and $10 with probability 0.01. This is a horrible lottery. What's the expected value of the lottery? Well, it's this, just what we wrote before. Well, there's two possible values in the support, 0 and 10. So you have 0 times the chance of getting 0, which is 0.99, plus 10 times the chance of getting 10, which is 0.01. The first term is 0, the second term is 0.1, so this lottery is worth 0.1. If this lottery costs more than 0.1, it's objectively a bad lottery. Now, you might still play it, as we'll talk about in the next module, if you're really, really risk-seeking, you just love lotteries. But if you're risk-neutral or even particularly risk-averse, you won't play this lottery if it costs more than 0.1. On the other hand, if it costs, say, a penny instead of a dime, if it costs 0.01, then people who are risk-neutral or risk-seeking will definitely play a lottery, and most risk-averse people might play a lottery too because it's a pretty good lottery. You pay a penny, and your expected value from the lottery is a dime. So in general, the lottery is going to, an expectation, multiply your money by 10. Note that in no individual case do you ever actually receive 0.1. That's what you get in expectation. That's your expected value. If you play this lottery 100 times, you would get 0 99 times on average, and 10 the other one time. An expectation that has a value of 0.1. So even though you never actually receive 0.1 in any given realization of the lottery, over time, on average, you would average out your total winnings to 0.1. And this is what we mean by expected value. It's the expected value of this thing, the average value you would obtain if you were to do it over and over again and sort of take the average there. That is expected value, and that's when you often use it. Okay, so that covers expected value. We'll talk more about the other common uses of this expected utility in the next module. Before we get there, though, the other really common usage of expectations that you see in stats this time is looking at the moments of probability mass functions. The moment, and this is the word moment, normal English word moment, the moment of a distribution is a parameter of the distribution, and it's related very closely to the other parameters we've already talked about. So for instance, the mean of a distribution is the expected value of the distribution. We often call that mu, the mean. This is the same mean we talked about before. This is the first moment of the distribution. In general, this is the kth moment of a distribution. Now, we often are interested not in the kth moment around 0, as this is called, but rather the kth moment around the mean. This here is the kth moment around the mean. This might seem kind of strange, but replace k with 2, and you have the exact formula for variance. If k equals 2, then this thing equals sigma squared, which is what we talked about before when we talk about variance and the parameters of distributions. This is a distribution. This is the variance of a distribution with k equals 2. Now, there are higher moments as well. These are the most common moments used by far. But there are higher moments as well. If we have k equals to 3, we get what's called the skewness. S-K-E-W-N-E-S-S, skewness. The skewness is a measure of how symmetric or asymmetric the distribution is relative to the normal distribution, which is completely symmetric around the middle. K equals 4, you get what's called kurtosis. I did not name these. You get what's called kurtosis. And the kurtosis tells you how flat or how peaked the distribution is relative, again, to the normal distribution, which has a certain characteristic flatness, thin tails in general, and peak like that. If it's very highly peaked, it'll come up faster than a normal distribution in terms of how fast it slopes up. And the tails might be thin. If it's fat tails, you have fatter tails in the end, and it'll come up more slowly. This is a different, although related thing to variance. Variance just variance doesn't change the characteristic shape of the normal distribution. It still has the same properties as always. It just changes how squished or how spread out it is. Kurtosis changes the actual width of characteristic things like how fat are the tails. Oftentimes we treat these higher order moments standardized to the standard deviation. So we'll divide each one of these things over here. I should have written that. If you divide this thing over here by sigma cubed for the skewness, or sigma to the fourth for the kurtosis, that gives you a standardized moment. Standardized third moment or standardized fourth moment, which often we are interested in looking at. That's it. And these are, again, common statistics. They are parameters of distributions. We often want to know if things, for instance, are represented well by normal distribution. So we might compute the skewness and the kurtosis and hope that they match what we get for normal distribution. And if that's true, then we should expect that a normal distribution fits our data well. If the skewness, for instance, is not 0, we would expect that the data don't match normal distribution well. So these moments help us understand how appropriately to model our data generating process and the data we generate from that process using existing distribution functions. And some of that might not have been clear yet because we haven't actually done normal distributions yet. It's just that these come up most often in comparison to normal distributions, which are continuous distributions, but they're also present in discrete distributions. For instance, we said earlier that the Poisson distribution, remember, which looks like this, or the probability that big Y equals little y is that. We said that first of all, mu was the sort of average frequency of observing things. That's the mean of the distribution. So if we find the first moment around 0 of this distribution, we should get back mu. We can do that as an exercise. So we're going to add up overall y from 0 to infinity. So impossible things we could have gotten. E to the mu. So y times e to the mu to the y over y factorial. The y now without the y out front, we know this should end up as 1. This thing over here is, when you sum it from 0 to infinity, it gives you e to the mu. That cancels with this thing. That gives you 1. That has to be that way because if you add up all possible outcomes, you should get back, you should get a probability of 1. Something must happen. So if you add all possible things that could happen, then the probability that anything could happen should be 1. When you put the y up front over here, you're taking expected value. So we can do this. First, we can pull out the e to the negative mu because that's not relevant. And you get this. Now you can divide through by y. That makes the y factorial on the bottom equal to y minus 1 factorial. We can make it match better by pulling out a mu. So we get mu times mu to the y minus 1, because remember mu times mu to the y minus 1 equals mu to the y minus 1 plus 1, which is mu to the y. And that, we can pull out the mu, and we get this. We get that sum over here from 0 to infinity, which is mu to the y minus 1 factorial. Now, so far so good, except we need this thing to become e to the mu. but it is. Why? Well, note that when you plug y equals 0, before, up here, in this equation over here, you get 0 times this. So actually, we shouldn't have written 0 this whole time. We should have written 1. Because the 0 actually goes away, right? When y equals 0, y times mu to the y is actually 0. So we can eliminate the 0 term in that sum, and all these down here should be 1. Well, this is an infinite sum, so this sum over here from y equals 1 to infinity of y minus 1 starts at 0 and goes to infinity. Right? If we replace y minus 1 with y, actually, let's be clearer, with z, then we get this thing going to the sum like this. Z equals 0 to infinity. So now remember, z is y minus 1. So it goes from 0 to infinity of mu to the z over z factorial. And this thing is e to the mu. So these things are 1, and you get mu. And this actually proves what we want. I'm not going to go through and do the variance. If you recall that the variance is also the same as the mean for Poisson distribution, I'm not going to do this for you right here, because it's not that important right now, but it's a good exercise to do. Here's a hint. The expectation of some k, in this case, or y, I guess, in some case, some y squared, is the expectation of y times y minus 1 minus y. Because this is y, this term over here is y squared minus y, sorry, plus y. And you add plus y, and the y's go away. Why do I need this? Well, expectations, because they're just adding things, are linear. Like the derivative was linear and the integral was linear. They're also linear. The sum is also a linear operator. Well, this is going to equal this. We just did this. That was mu. And in fact, I think I'm just doing this all for you because I'm getting carried away. What's this thing? Well, we can do the exact same thing again. Yeah, I'm just going to do this for you. You get this term over here becomes y equals 0 to infinity of y times y minus 1 times e to the negative mu times mu to the y over y factorial. Now the first two terms in the sum are 0. When y is 0, the whole thing is 0. When y is 1, because this is 0, the whole thing is 0. So this actually equals e to the negative mu, the sum from y equals 2 to infinity of e to the negative mu squared mu to the y minus 2 over y minus 2 factorial. Again, we can replace y with z, where z is y minus 2. Then the sum of this thing is e to the mu. That cancels with this. Oh, too many e to the mu's here. Sorry. It's already out here. That cancels with this, and you end up with mu squared. So this whole thing is equal to mu squared plus mu. Now it turns out that the expectation of around mu of this equals the expectation multiplying out of this. Mu is a constant, because mu is a constant in these things, so expectation of y squared minus 2 mu expectation of y plus mu squared expectation of 1, which is just 1, equals mu squared plus mu from the previous slide minus 2 mu times mu squared, sorry, 2 mu times expectation of y, which is mu from before, that's the mean, plus mu squared. We have 1 mu squared, 2 mu squareds, minus 2 mu squareds, that equals mu. So there you go, I did it anyway. This is the expectation. This is the variance of the Poisson distribution, which is the same as the mean. Again, we calculated the second moment around the mean to figure out this. Now, one last thing which is really useful for expectations in this regard, if you take this line and forget about the whole distributions, what you get is the expectation of y squared minus 2 times the expectation of y squared, because mu is the expectation of y, plus the expectation of y squared, because again, mu is the expectation of y, so you square it. That equals expectation of y squared minus expectation of y quantity squared. And that's a very useful, this thing in blue up here equals this thing underlined in blue down here is a very useful identity for working with variances and expectations. Okay. Well, that's more than I intended to do, but I hope that was helpful, and that's all we talked about for moments of discrete distributions. We'll mention this briefly for the continuous, but not very much because it's the same exact logic, just with integrals. And then last module of this lecture, we're going to discuss expected utility, a special class of this expectation. Thank you very much.